Our topic is volatility spillover in cryptocurrency markets. Over the past decade, the cryptocurrency market has expanded rapidly with the number of assets on the market increasing dramatically. In particular, major coins like Bitcoin have a dominant market share, and the price fluctuations often significantly affect smaller cryptocurrencies. This volatility spillover not only reflects the market price, but also reveals the systematic risk with the market. Therefore, understanding how large-cap cryptocurrencies affect small-cap ones is crucial for investors, risk managers, and policymakers. Firstly, the research questions are spillover direction. Does the volatility change of large-cap cryptocurrencies significantly influence the volatility of small-cap cryptocurrencies? Spillover intensity. How do different large-cap cryptocurrencies affect small-cap cryptocurrencies, and how do they rank in terms of spillover strength? Reverse spillover. Is there evidence of reverse spillover from small-cap cryptocurrencies to large-cap ones? To answer these questions, we use the vector autoregression model, VAR, which captures the dynamic interrelationships between asset returns. We also use forecast error variance decomposition to analyze how each cryptocurrency contributes to the overall spillover. Additionally, we apply the rolling window method to capture how spillover effects evolve over time, especially during market volatility. Lastly, regarding the research significance, through this research, we aim to help investors understand the interrelationships between cryptocurrencies and provide quantitative evidence to optimize asset allocation and risk management strategies. Furthermore, we believe our finding will offer empirical evidence that can assist policymakers in understanding the systemic risk in the crypto market and provide support for effective regulatory policies.
Hello everyone, today I will briefly review the key studies that shaped our analysis of volatility spillover in cryptocurrency markets, which is how shocks move between assets and where our research adds something new. Angle first introduced the concept of volatility spillovers using high-frequency yen-dollar data and graph model. They show that shocks in one market quickly spread to others, which they call the meteor and shower effect. Diebold and Yamat extended this idea with spillover index, a Vera-based framework that quantifies total and directional spillovers. Their evidence using the 2008 crisis confirmed strong global interconnectedness. Finally, Forbes and Rigbone argued that many so-called contagion effects are actually due to rising volatility, but not true crisis, which is an insight that helps us interpret crypto interdependence today. And moving to cryptocurrencies, Corbett described extreme volatility and speculation, while Ball and Dipfa and Karsiempa found the Bitcoin volatility to be persistent and asymmetric. High-frequency modeling developed by Andreessen and Boleshev and later adapted by Lealsa now allows spillover analysis at the intraday level. Yet most studies still focus on Bitcoin and Ethereum, using short samples and ignoring small cap tokens or reserve spillovers. So our project filled this gap by analyzing 12 cryptocurrencies across 25,000 hours of high-frequency data, testing both large to small and reserve transmission and linking spillover to systematic risk. In summary, earlier research explained how volatility spreads, and our work shows where and how fast it spreads in the crypto ecosystem. By extending classical model with richer data, we capture a clear, real-time view of interconnected digital markets. That's all of my content of my part. Thank you very much.
Having revealed the lecture and identified the existing gaps, which framework is best suited to address these challenges? The VAR model is our chosen framework. The model is specified as follows. YT is a 12 times 1 vector containing annualized realized volatility for cryptocurrency. C is a vector of constants. Phi acts as set of dynamic weights, quantifying how much influence the volatility from I periods ago has on the present. P is the lag. E represents the error. We choose this model for a key reason. It is perfectly suited to capture dynamic interdependency among all 12 cryptocurrency in our studies. Unlike simple model, the VAR allows us to see the past volatility of every single currency from Bitcoin down to small caps, influences the current volatility of every other currency. A major advantage of VAR is its flexibility. It treats all variables as endogenous, meaning we don't have to pre-specify which coin is the leader or the follower. It is crucial for our research, as one of our key goals was to test actual influence relationships, rather than just assuming Bitcoin is always the dominant force. This estimated VAR is the foundation of our analysis. It serves as the input for the tools we use next, namely impulse response function and forecast error variance decompositions. These tools built on the VAR allow us to find the spillover effects with precision, uncovering their direction, intensity, and how long they persist. Now, let's walk through the 4 key assumptions underlying our VAR model. First, stationarity. This means the data should have stable mean and variance over time. It's a fundamental requirement because non-stationary data can lead to spurious regression results, completely invalidating our findings. To test this, we conducted ADF tests on all 12 volatility series. The results were clear. The unit root hypothesis was rejected for every single cryptocurrency, so we can confidently say this assumption is satisfied. The second assumption is linearity, that the relationships between these volatilities can be captured by linear equations. This is necessary for our impulse response and variance decomposition results to be valid. We acknowledge the real financial market can be non-linear. However, for establishing the channel and strength for spillovers, a linear VAR is a robust and standard starting point. Thirdly, we have homogeneity. It assumes the model's parameters are constant throughout our sample period. It is crucial for consistent economic interpretation. If parameter shift, our spillovers measures becomes an unreliable average across different markets. In reality, the crypto market is known for structural breaks. We acknowledge this limitation and in future work propose robustness checks such as rolling window estimation to formally test for stability. Finally, normality of errors. This assumption is most important for validity of our hypothesis test. While ideal financial data often has fat tails, violating strict normality. The key here is our very large sample size, over 25,000 hourly observations. This allows us to rely on central limit theorem, which ensures our test statistics are valid asymptotically, even if errors are not perfectly normal. So we have validated the critical assumptions and knew the potential limitations. Now we can move to data description and formal analysis.
Our data comes from Binance Exchange API, collecting 5 minutes OHLC with candlestick data. We choose 5 minutes intervals to capture intraday volatility patterns while avoiding microstructure noise. The sample spans from October 19, 2022 to September 30, 2025, covering nearly 3 years of complete market cycles. We selected 12 cryptocurrencies stratified by market cap, 3 large cap, 5 mid cap, and 4 small cap coins. Data quality is excellent with missing rates below 0.1%. We use forward fill to handle missing values, which prevents future information leakage and preserve temporal causality. We first calculate log returns using the formula RT equals log PT minus log P bracket T minus 1 bracket. Log returns offers 3 key advantages: time additivities, normal distribution of approximation, and systematic treatment of gains and losses. Next is our core variable realized volatilities. We group 5 minutes returns by hour, that's 12 observations per hour, then calculate RV as the square root of the sum of squared returns. This is based on the Anderson and Bolivar's 1998 theoretic framework. For comparabilities, we annualize hourly RV by multiplying by 77.77. Our statistics reveals a clear market capitalization gradient effect. Small cap volatility is 2.1 times that of the large cap coins, confirming the negative correlation between market cap and volatility. Large cap average RV is 36.24%, showing stabilities. Mid cap is 63.65%, and small cap reaches 77.5%. Bitcoin shows the lowest volatility at 31.05%, while FET reaches 92.31%, and OP hits 78.57%, demonstrating the highly speculative nature of the small caps. This clear gradient patterns establish the foundation for our volatility spillover analysis.
In this section, I will present our data analysis on volatility spillovers across 12 cryptocurrencies between 2022 and 2025. We constructed hourly realized volatility from 5-minute Binance data, tested for stationarity, estimated a VAR model with 8 lags, and then measured how shocks spread using forecast error variance decomposition. Let's start by looking at how volatility behaves across different cryptocurrencies. Figure 5.1 shows the average realized volatility for each cryptocurrencies. We see a clear upward trend. Volatility rises as market capitalization decreases. Large cap coins such as Bitcoin, Ethereum, and BNB are relatively stable, while smaller coins like FET and OP experience much higher fluctuations. This inverse relationship between size and volatility reflects higher speculations in smaller caps assets and aligns the earlier findings by Corbett et al. 2018. So overall, large coins are safer, smaller ones more volatile, exactly what we would expected in a speculative market. Before estimating the VAR model, we confirmed that each series is stationary. In figure 5.2, all ADF statistics are well below the 5% critical values of negative 2.86. So the null of a unit root is rejected. Using the Bayesian information criteria, we selected 8 lags, meaning volatility shocks persist for roughly 8 hours before fading. This provides a strong model fit and captures short-term dynamics without overfitting. Figure 5.3 summarizes the forecast error variance decomposition result. In other words, how much of one asset's volatility is explained by shock in another's. There's a clear hierarchy. Large caps to medium caps accounts for about 14%, large to small about 11%, medium to small around 8%, and small to large only 3%. This means Bitcoin and Ethereum act as the core risk transmitter and volatility flows downwards through the market. The pattern mirror the core to periphery contingent structure described by Diebold and Yeomans 1T12. To summarize, Bitcoin and Ethereum dominates the volatility network. They are the main source of risk, spillover cascade from large to small coins, and last roughly 8 hours. Because of this strong connectedness, diversification within crypto is limited. That means when the Bitcoin moves, the rest of the market follows. In short, monitoring large caps volatility can serve as an early warning signal for market-wide instability.
In conclusion, first, we definitively established that Large cap cryptocurrencies do significantly influence mid and small cap volatility with an impressive 92% spillover success rate. 11 out of 12 spillover paths proving significant. Our results show that large caps explain between 34 to 55% of small cap variance. This demonstrates a clear hierarchical influence structure in the crypto ecosystem. Second, we uncover an unexpected ranking in influence strength. Contrary to market cap expectations, BNB emerges as the dominant influencer, affecting all 11 tokens at 100%, followed by ETH at 91%, and surprisingly, BTC ranks third at 82%. This reveals that exchange ecosystem centrality may be more critical than pure market capitalization. Third, we confirmed that reverse spillover do exist, identifying a significant path where mid and small cap tokens influence large caps, particularly through field counts affecting all major cryptocurrencies. Our key insight centers on the repeat transmission speed, with spillover occurring within 3 to 4 hours, combined with the high network density of 69%. This creates significant systemic risks across the cryptocurrency market. Thank you.